This is the closeout and synthesis of NESP, Earth Systems and Climate Change Hub Project 2.3 Component 2, focused on decadal scale predictability of ocean temperature extremes. And it links with Component 1 of this project, which is run out of CSIRO on towards an access decadal prediction system. My name is Neil Holbrook and I'm the Chief Investigator of Project 2.3 Component 2, and I've been ably assisted by Dr. Eric Oliver as my Deputy Chief Investigator throughout the project. The project's been led out of the University of Tasmania and has been linking with CSIRO Oceans and Atmosphere in Component 1. And the climate challenges addressed by this project are fundamentally in the extreme space, but also some links to coasts. Well, ocean temperature extremes can be devastating for fisheries, aquaculture and ecosystems. And tracking and being able to predict these extremes is key to managing and potentially reducing their impacts. So with that problem in mind, this project set out to address really two key goals. The first goal was really to understand the predictability of ocean temperature extremes on timescales greater than a year. And thinking about the decadal prediction system, the timescales that the decadal prediction system is looking at is 1 to 10 years. And secondly, to identify detectable changes in marine heat waves above natural variability and whether humans may have played a role or may have contributed to increasing their likelihood. So how did we address these goals? Well, firstly, we wanted to look at potential predictability of ocean temperature extremes, and this is really a property of the ocean and the climate system. And the second is really to look at forecasts from the Access Decadal Prediction System developed out of CSIRO. And in the next part, in terms of detection, look at globally detectable trends in marine heat waves from sea surface temperature, and also apply a fraction of attributable risk analyses on Australian region marine heat waves to understand whether the scale of those marine heat waves are more likely due to climate change. From the project, there are many publications that this project has contributed, and you can see those up on the screen. And these include impacts of marine heat waves, how they threaten global biodiversity and the provision of ecosystem services, looking at trends in marine heat waves, human influences, whether they are more likely due to anthropogenic climate change, the dynamics and drivers around ocean temperature extremes and marine heat waves, and ultimately also their predictability. The project has produced 10 published papers, 3 are submitted, 1 is in preparation, and 4 reports. So the project has a number of outcomes. Firstly, we've identified that there are important timescales and locations of ocean temperature potential predictability around Australia. And this figure up in the right here, in a paper that's in preparation currently, shows the type of timescales that ocean temperature can be potentially predicted if we had a perfect model of the climate system. So you can see that we can go from maybe up to 3 years or so here in the west to possibly 7 years or so down in the southeast. And this is just based on the analysis of sea surface temperatures and our understanding of its connection with climate modes. Secondly, the Access Decadal Prediction System provides forecast potential of ocean temperature extremes in key Australian regions on multi-year timescales. We've looked at a couple of sites in particular. This figures here that are shown here shows the observed sea surface temperature anomalies in February of 2010. And this decadal forecast here from the Access system shows a 3-year out simulation, a forward-looking forecast for that same period. And you can see that while the boxes are a bit coarser, the overall characteristics are somewhat similar to the February 2010 observations. But we could take this potentially further with the right type of downscaling. Dynamical downscaling may add further value to forecasts for decision makers at the scales that are relevant to them. For example, if we took a forecast or a projection forward in time and dynamically downscale this into the shelf region, as has been done here in this paper. You can see down to 2 kilometre scales, we're starting to get the circulation that people really care about. We've also identified that there are detectable observed trends in global marine heatwave frequency and duration. And this figure up here in the right shows some results from that work, where you can see here in red, these are satellite observations of sea surface temperature trends here in frequency of marine heatwave days. But here, sort of a proxy representation through to the early part of the century shows how it tracks back to then. We've also shown that marine ecosystems are impacted more by marine heatwave events than trends. And this figure here on the right shows seagrass density in Australia. Here's some seagrass. And you can see here marine heatwave days per year. As you increase those marine heatwave days per year, you can see that the seagrass density seen in the observations has actually gone down. And we've also shown that severe recent marine heatwave events around Australia of the scales that have been observed are now more likely due to anthropogenic climate change. So in particular here, this Tasman Sea marine heatwave in 2015-16 was incredibly long, it was unprecedented, and the analysis showed that the probability of marine heatwave of that scale was more likely due to climate change. So benefits of the project, well, ocean temperature extremes can indirectly or directly impact things like oyster through virus, salmon and abalone. And the 2015-16 marine heatwave compromised all of those species. With that in mind, strategic decision making is possible from skillful forecasts. So it's fair to say that marine industries can benefit from skillful forecasts on timescales from days to years. For example, on short timescales, it might be possible to take oyster out of the water if we have a short timescale forecast that is skillful. Whereas on sort of seasonal to multi-year timescales, that can assist planning. One of the benefits is also that the potential predictability of ocean temperature extremes in various regions around Australia is greater than 1 year and even a few years. And that is also an important property for potential planning and development of forecast systems. While the excess decadal prediction system simulations do indeed indicate, at least from these preliminary outputs, that multi-year forecasts of ocean temperature extremes are likely to be possible and beneficial. So among the achievements from the project, we've improved understanding of ocean temperature extreme trends and human influence. We've provided information around the potential predictability of ocean temperature extremes, predictability on greater than 1 year timescales from the Access Decadal Prediction System. And we've also contributed to generation of a categorization scheme of intensity. Findings contribute to the goals of the International Commission on Climate. We expect several publications to be cited in the IPCC 6th Assessment Report. There's been 2 separate NESP Hub science seminars given by Eva Cugnon and myself, one in 2017 and in 2019. And there's been a joint ARC Centre of Excellence and NESP Hub briefing note on marine heat waves, along with the other publications that I mentioned. So the next steps, well, this project will feed into RPV5, project 5.8, entitled Marine and Coastal Climate Services for Extremes Information. And in that project, we intend to examine 3 to 4 case study locations and critically review relevant literature on vulnerability to ocean temperature extremes. We intend to survey stakeholder knowledge via questionnaire or workshop. We also intend to estimate ocean temperature extreme probabilities over the shelf and or near to the coast, and also create some storylines on these case studies. Thank you all for listening. If you have any questions, don't hesitate to contact me on either email or via phone.